Okay. So continue with the thermal conductivity. So this thermal conductivity, you can see that's related to the energy equation. So basically, energy equation usually we use in the, we have like the heat, and the heat related to the temperature difference. So if we only have a purely work, that means we only have a purely force. Usually we will use the momentum equation only, and the momentum equation we converge with the energy equation, because in this kind of a case, if you don't have a temperature difference, you don't have a heat, and basically only energy is come from the work. So for the temperature difference case, usually this heat flow we will use the Fourier law, and this Fourier law based on the temperature difference gradient and also the thermal conductivity. So you can see this will come out what kind of parameter? The gradient temperature. What this will come out? This is vector calculus. Yeah, they will come out a vector. And this with some kind of coefficient. So this coefficient, sometimes they will relate to the direction, sometimes they will without the direction, because we are talking about isotropic. So opposite isotropic usually is isotropic. They have a certain of a direction, it's more preferred. In a solid, usually they have a certain of a preferred direction. But for the fluid, because fluid is quite equal, okay? So they don't have a preferred direction. So that means you can in the x, y, z direction, we can use the constant as that. So for this, we will have this heat flow. Then here I just like to remind of you. Usually the power, this is related to the rate of energy. No matter the rate of heat or rate of work, usually this related to the power. And also combination about this unit. Usually we will mention this as power flux. Okay, some similar you can have a different kind like a heat flux, because they relate to the unit area. So they have a very special current. It's a flux. So this is just some kind of maybe technique current. So this thermal conductivity, similar like a viscosity, is some thermodynamic property, and use the corresponding state, this principle. Usually we can estimate their relationship as well. From here you can see the thermal conductivity, their relationship with viscosity. This is quite famous. Non-dimensional parameter, so-called Prandtl number, and this Prandtl number is related to the. You can see that related to the two property. If we make some kind of simplified, original form is like this: dynamic viscosity, specific heat, and thermal conductivity. But we sometimes we will use the kinematic viscosity to replace the dynamic to replace the dynamic viscosity. And here we need to use the thermal diffusivity to compare with this the kinematic viscosity. Okay, so basically they have the same unit, but they also have some or same kind of physical mechanism. From this, usually they represent the momentum diffusivity. So that means they represent how fast this kind of viscosity diffuse into the flow. So for the flow, usually you have some kind of distance or time need to diffuse. One of the example is like if you have a pipe flow. Okay, so here is an example for the momentum diffusivity. So for the momentum diffusivity, we can see if we have some pipe flow at the beginning, at the entrance, they have a uniform flow, but they need to take some time to diffuse their viscosity effect to certain of a distance. And usually this distance we mention as entrance length. Laminar flow, turbulent flow have a different entrance length. This is related to this viscosity. You have a different viscosity that's related to how you diffuse your viscosity, because they will relate to the motion of your neighborhood fluid. Similar for the thermal diffusivity, it's like we have different temperature, and this different temperature they will diffuse to the neighborhood fluid. So the Prandtl has a very significant contribution to which is kind of a theory? Do you have an idea? Basically, in the 20th century, there is a very important theory in the fluid mechanics. It's like the boundary layer theory. So this is, I think it's a very quite significant contribution in the near century in the fluid mechanics. The boundary layer theory, even right now, there's a student of Prando, there's a book talking about the boundary theory. It's still in the many schools as a textbook. And you can see the boundary is like this dotted line. Because the boundary layer, for the momentum boundary layer, they are influenced by the viscosity, influenced by this kind of dynamic viscosity. So similar, there is a boundary, so-called thermal boundary, that will influence by the temperature of a neighborhood. So Prandtl number basically is used to compare these two boundaries. Okay. So another story is about Prandtl. Prandtl is another very famous student. It's von Karman. So it's also in the last century for the aerodynamic. So the airplane, the rocket, this kind of design is quite related to the von Karman distribution. And the von Karman even get some kind of how to say, they issue some kind of military. So he's some officer in the Air Force in United States, but he is not joining the Air Force. But because his contribution about the aerodynamic, so they issue some kind of officer of Air Force to the von Karman. There are many students of von Karman as well. Even in China, there is a very famous scholar named like Chen Xuesen. This is a student of von Karman. Later on, he went back to China, and right now the satellite, airplane, missile are related to his development. Okay. Okay, so I think pretty much is about the thermal conductivity, because we are talking about diffusion. So diffusion, also the mass, they will diffuse. For example, if you put some perfume, and later on, whole classroom will smell this perfume. So this is related to some kind of mass diffusivity. Okay, so similar momentum diffusivity, thermal diffusivity, they are same mechanism. One more thing is you can see this diffuse direction is normal to the motion direction. Your motion is in the x direction, but diffusion is in the normal direction. So basically, this part without any motion, but this diffusion is due to the viscosity that push or pull the neighborhood fluid. Okay, so similar thermal diffusivity is said that use this thermal conductivity to transfer the energy due to the temperature difference. So from a high temperature to a low temperature. So mass diffusivity is same mechanism. They have a high concentration. They will go through to the low concentration area. Okay, so related to the mass conservation equation, of course, we have mass diffusivity. So you can see previous, like the momentum diffusivity is related to the momentum equation, and the thermal diffusivity is related to the energy equation. So in this mass diffusivity, usually we are consider the concentration. So this concentration, sometimes they will represent as a volume concentration. So this volume concentration is like the total volume, and in this spaces, how much mass in this spaces, then we will have spaces density. So sometimes we will use the mass concentration. Use this and relate to the total density. So this representative is like the spacious mass compared to the total mass, because your volume are the same. So they have a different way to represent this kind of concentration. So fixed load usually represent like this way. Your mass flow rate in the unit area is related to your this kind of a concentration gradient. So your concentration gradient will determine the different kind of direction for this mass goes through. And the coefficient of mass diffusivity in this case, they have the same dimension like the momentum diffusivity and for the thermal diffusivity. So if we want to compare the diffusivity, for example, by the mass, or by the momentum, or by the thermal, then we come out different kind of dimensional parameter. Okay, so this is for the mass diffusivity. And another additional parameter I like to introduce is the thermal expansion for the fluid. Okay, so the last transport property I like to introduce is thermal expansion. So for the fluid or for the gas, basically we all have this thermal expansion coefficient. Then this parameter is especially in the natural convection problem is quite important. For the seawater, usually they have this kind of natural convection to transport different area of water. Then basically they maybe due to the temperature difference, then they will have a different density. Then or they have a different kind of salinity, so they have a different density. So they will convection in the ocean. For the air, similar. We have a different kind of temperature of air. That we have this kind of air mass change. If your air mass didn't change, your air usually will be polluted very serious, especially in the industry area. So this kind of convection sometimes caused by the natural convection, sometimes caused by the forced convection. And the natural convection we classify as a buoyancy-driven convection because they have a density difference. They have a buoyancy force to cause this kind of motion. So come up another question. We have a forced convection. So forced convection, what kind of force driving the flow? Pressure? The forced convection. You create some kind of wind, or you blow some kind of flow. Okay, so yeah, you maybe create a pressure difference, but basically you give the flow certain of a velocity. You give this kind of velocity, so basically the flow particle they have some constant velocity. So for example, you want to cool in this, you blow certain of a velocity of air. So basically, you give this kind of fluid particle some kind of inertial force. Maybe you use the pressure, maybe you use a different way to give their velocity. As long as they have a velocity, they will have a so-called inertial force. So why they call it inertial force? I find some students don't quite understand what's inertial force. So this natural ventilation usually is a buoyancy-driven convection. Forced convection, this is related to the inertial force. This is inertial force, convection. But what's inertial force? Let's come to the Newton first law, right?
So if you, for example, you push these in this direction, so if your force is in this direction, so the object will move in this direction.
Yeah.
So basically, if you have a fan, right? The fan just like blowing air, so the air is in that direction, so and it will come to you in this direction.
Yeah. So basically, why they call it inertial force? Because we create this kind of constant velocity flow. So this constant velocity flow, if there is no external force, that's Newton's first law tell us, stationary always stay stationary. Constant velocity always keep constant velocity unless there's external force. So external force will come to the second law, right? Second law, external force become to the acceleration of a particle. But from here, because you create a constant velocity, so constant velocity make this motion. So that's why we mention this as inertial force. So you can see most of the non-dimensional parameter, they will relate to the inertial force. For example, Reynolds number, they are inertial force compared to the viscosity force. So that means what kind of velocity come in, then viscosity, how to change this kind of original motion state. So similar for the rest of non-dimensional parameter, most of the dimensional parameter, they are compared with the inertial force because they have some kind of reference motion or reference kinematic condition. They are compared with under this kind of condition, what kind of another force compared with this inertial force. Okay, so inertial force basically, because you create this kind of constant flow, if there is no any body inside this flow field, the flow will keep constant velocity. So that's different from this. This is driven by they have a different kind of density, and this different density will create a different kind of buoyancy force. So thermal expansion is defined like this. So it's compared to the original density, and when the temperature change, how the density change rate. So if we use the perfect gas or ideal gas, so this kind of equation, then we can get your thermal expansion is like 1 over T invert. The equation is like this. But remember, you should use the Kelvin scale. Because the ideal gas equation, you are always use the Kelvin scale. Then I have another question for you. Because you guys are engineers, suppose solving the question, solving the problem, right? Because you are not in the physics and not in the chemistry, mathematics department. Usually in this department, they are supposed to find the problem. So right now I give you a question is, how about thermal expansion for the liquid? If I have a liquid, for example, I have water, or I have the oil, can I use this equation? The first, I cannot use this equation because this is called ideal gas. It's not ideal liquid, okay? Second, if you have this problem, how shall you do? How should you solve this problem? Yeah, because the last hour I asked one question and your answer made me feel quite interested. So similar, if you have this problem, what should you do? For example, water is the most common liquid. Then if you the water, how you look for the thermal expansion for the water? way, do you know my question? So, what's the question?
查表，可以用查表。
Yeah, look for a table. Usually, like this kind of problem, you just look for a table. This is some kind like a look for previous people note or look for previous people organized data. So for the table of water density with temperature, that's quite common. And also water with a different salinity. For example, like a different seawater have a different density. That's quite common. So usually for this kind of I think for this kind of a common problem, supposedly you should be able to solve. Because I have some undergraduate student, they maybe go to some company for like an internship. The people will give them very practical problem. For example, how to design the transport water or how to transport air and which kind of a motor they need to choose. Then this is a very practical problem. So if you don't use your previous knowledge, I think your undergraduate will give you some previous knowledge. Then you should look what kind of a knowledge is like what kind of a tool you already have. Then try to use the previous tool and think about what kind of a tool you still shoulder. You maybe need to make up some kind of a new tool, but you are not without any weapon. You already have some training in your undergraduate, maybe high school. They will give you some kind of basic knowledge. And this knowledge mostly, just like I previously mentioned, mostly from the textbook, from some kind of a reference book. So how to use that? Because you are going to do the research. That's another different level. How to use this previous knowledge to attack new problem or old problem. But mostly previous people already done some. How you based on previous people's best to give new contribution. So that's more important for you in the graduate school. Okay. Okay. So we take a break. Then later we will go to another new topic about the vector calculus.